we talk about Noether's theorem. So we went from classical mechanics to classical field theory. So let's review just a little bit the classical field theory one. So we have a Lagrangian that depends on our fields. And we imagine that there is a nice, very interesting variation that we can make on the fields so that the Lagrangian happens to be a total derivative. So if we consider stationary points, of the action, then we concluded that the following object had to be let's see, 0. So the derivative of this object had to be 0. And we said, well, that this was, we could call this a conserved current. We also said that once you have a conserved current, you could define a conserved charge by just integrating over the space the 0th component. And from here, we can learn that the total derivative with respect to time of this quantity is 0. Now, yesterday, Andres asked a question. And the question was, well, what happens if you add something to this that vanishes for some reason that is trivial? So can we come out with something that vanishes for some reason that is trivial? Well, imagine that you shift your J by something that looks like this. Take a derivative with respect to nu of some quantity made out of the fields, but that happens to be antisymmetric in the indices. Sorry, the minus signs. Yes, that's too much antisymmetry.
The conserved charge Q, that's not a Lorentz thing, because it's the integral of the 0 component of the portion.
Well, try to think about it. Try to think what happens when you apply a Lorentz transformation, okay? Very good. But now, let's keep going with Andres' question. So imagine that you do this. You find anything, any antisymmetric tensor that you want, made out of the fields, take the derivative, and put it in here. Now, did we spoil the conservation? Well, clearly, the operator acting on this will give you 0. And now the operator acting on this will also give you 0. Because this is symmetric, and this is antisymmetric. Okay? Now, what's the consequence of this on the charge? Well, let's see. So Q prime would be the integral d3x of the all current plus d3x of the new contribution. So we will have derivative with respect to nu, of 0 nu. But this object is antisymmetric. So if this component is a time component, this component can only be a space component, right? It's antisymmetric. So if I put a 0 here, I get 0. So this object is really just a derivative with respect to I. I'm summing over I of 0i, because the 0 part is 0, because it's antisymmetric. Now this is nothing but the gradient, the divergence of a vector And again, my assumption that everything vanishes at infinity fast enough implies is that this is 0 by Stokes' theorem. Okay? So we find that our conserved charge is actually the same as before. Okay. Very good. Now, what do we want to do? I said last time that we were going to have an example. We're going to work on an example. And it's going to be a very physical and important example. But for that, we have to understand a little bit something about symmetries. What we want to do, we want to perform a translation. But there are two ways of thinking about translation in space-time. One is a passive point of view, and one is an active point of view. You can think about having your physical system and translating the physical system. Or you can think about just saying that you have a reference frame, you're measuring everything from here, and then you decide to shift and change coordinates to a new coordinate system and describe the same system, but now with a different coordinates. Okay? So one of them is called active, and the other one is called passive. The active one is where you take the physical system and shift it, and the passive one is where you simply think about changing coordinates. Now, of course, if you have an infinite system, I guess it's going to be hard to do something to it. So you might want to think about the passive point of view. So we're going to think about the following. Imagine we have, in space-time, we have a point x here. And we think that at this point, there is something that we describe by the value of a field. So this field has some value at the point x. Okay? Now I'm thinking about this. I'm going to think we have only been discussing scalar fields. So this is going to be a scalar field. And we're going to see what we mean by that. What we mean by that is that if you now decide to go and describe the same physical system using another frame or another coordinate system related to the previous one by a shift by a vector b, sorry, we're in 4 dimensions, so it could be just a vector b. So this system is the system prime, say. So the same point in space-time will be described. So now we're going to run into trouble. Let's call this x, and this is going to be x prime. Okay? Now, the value of the physical quantity at this point should not change. It's just the value of that quantity at that point. So if we have another description, and we ask what's the value of the physical quantity at this point, we should definitely get the same answer. Okay? So whatever the new description of this field is, must be such that it agrees or it gives you the same physical value at that point. Okay? But now we see from here that this point x as a vector, so how is it expressed in terms of the other ones? Well, you could say that x is the same as x mu. So what do we get? Minus b. Very good. Okay. So we have that our field at x minus b has to be equal our field at x. Now let's actually shift this backwards so that we get the new field after performing a translation. So let's shift so that we get the new field, say at some position x, in terms of the previous one. Okay, so this relation must also hold. So this is a way this object would transform if it's a scalar field. Okay? If we have a vector field, of course, something else will also happen, depending on the transformation we make. But for the time being, let's only consider the scalar fields. Now, under this transformation, if we ask what's the variation of the field, what do we have to do? Well, we have to Taylor expand this, assume that B is infinitesimal, okay? So let's assume that. So from here to here, we're assuming that B is infinitesimal. So we can Taylor expand this. So if we Taylor expand this, we're going to get something that looks like the derivative at x times our infinitesimal quantity. Do you agree? Plus higher order terms, but if B is infinitesimal, the rule tells us not to do anything with the rest. So the variation is nothing but phi prime of x minus phi of x with an infinitesimal value. So it's simply given by this up. Okay, so we learned that every time we have a scalar field, it transforms like this under a translation by a vector B. Now, is this a symmetry of the action? Say, of the Klein-Gordon action? Yes, it is. It must be, because we want something that is physical. So it should also be, just like translation of the blackboard up and down also seems to be a symmetry of this thing. We also want to impose that. But let's see it more precisely, okay? Imagine, well, the condition that we had something that is invariant under Poincaré was an action that is invariant under Poincaré. Remember, the measure was a d for x, so that's already invariant. And the Lagrangian density, therefore, has to be something that transforms up to a total derivative. Otherwise, we will not get that the action is invariant. Okay? But what is a Lagrangian density itself? What do you think? This thing depends on the fields. So the Lagrangian density is a field too, right? I mean, it's just a complicated collection of fields. But the Lagrangian density by itself is a field. So L is a field. What kind of field is it? How does it transform under the Lorentz group? It's a scalar field. But I told you that any scalar field transforms like that. Right? We didn't assume anything about phi other than saying that it was a scalar. So if L is a scalar field, then this implies that under a translation, it must be that the variation of L happens to be exactly the same as that formula. Isn't that nice? It's starting to look like what we need, exactly, right? Very good. But let me rewrite this a little bit. We want to rewrite it exactly as we got it there. But remember, that thing that we wrote there was for a transformation, for a single transformation. So we can think about translating in every direction in space-time as a different operation. Okay? So we can think about B translating in the x direction as being a single one. So for a single value of this index, we should be able to rewrite the Lagrangian as a total derivative. So I'm going to introduce a little trick in order to do that, which is just simply saying that nothing really interesting has happened, right? Other than saying that this is now my f mu, okay? And for every parameter, for every translation, I have a new object, okay? Very good. So now we can construct our conserved currents. So the conserved currents
Freddy, I'm a little bit confused. Why couldn't you identify L, B, mu as F? Like, why do you have to introduce eta?
Well, because I said that for every, if you just do the translation in the x direction, you should get a conserved current, right? So if I only did that, there is only one non-zero component here. Say the x component. So this would be x, and this would be x. So we need 4 conserved currents, okay? So that's how we're going to do it. In fact, each conserved current is going to be labeled.
You still have the same problem, because if B nu vanishes, you still get a vanish.
Well, it doesn't matter. It's a total derivative, as you can see beautifully.
But I guess I don't understand how one thing is different than the other. Because it's still going to, yeah. Like the argument you use.
Well, if it's identical to the other thing, then don't worry. It's the same, right? There must be a reason that I'm, this is an identity. I'm not saying that there is anything deep going from here to here. I'm just telling you, trying to give you a reason why I'm writing it like this. Because I want to think about each B as an independent object, okay? So, as I said, we should get a current for each transformation that we can perform, and we have 4 transformations. So we have an index that labels the transformation, and one index that labels the current, the fact that the current is a vector, okay? It just so happens that the 2 indices are the same kind of index, right? But, well, that's an accident. But, so if we now look at that object, we have we put a phi here, and now our variation, our fancy variation is something that can be in any of the directions, okay? So this variation is something that looks like that, okay? The variation of phi is something that now looks like that. Let me actually put this index up and this index down. Well, let me put it down and this one up. Sorry about that. So I'm treating everybody at the same time, but it's clear that B can be any vector, so it could be in the x direction only or in the y direction only, and so I'm going to get different currents. Sorry, now there is this index, and this index doesn't appear here. So what do you think I should do? And one thing that I could do is to put a B nu here, right? To collect everybody together into a single object, okay? Then I have to subtract this. Which again is a little bit annoying because I have the index down, but I can put it down here and put it up. No problem, okay? This thing is a delta mu nu, right? But this must be true, this equality must be true for any values of B, okay? So if I can factor out B nu from here, I can get the expression for my current. And actually, this current is so important that it has its own symbol. So this current, its symbol is called T, and it's the derivative with respect to this of nu phi minus delta mu nu. So I told you that this was very important. It has its own symbol, and therefore it has its own name. It's called the energy momentum tensor. Okay. Now, if we have currents, we should also have conserved quantities if the integrals converge. Okay, so what are the conserved quantities? Yes?
One question. Is there anything special in being global translation? Because, for example, if I take B to be dependent on the position,
yes.
I can always derive the same expression, right?
No. If B now depends on the positions, there are many places in the derivation of this formula where we assume.
But if I make a variation of my action and assume that E depends on the position, I can get to the same.
There could be theories where that is a symmetry, right? In fact, there is a theory in which that is a symmetry. It's actually a redundancy, more precisely. In general relativity, you can make general coordinate changes, and the physics shouldn't change, right? But in that case, every time you have something that becomes local, it's signaling that what is really happening is that you have a redundancy. It's not quite a symmetry, meaning that the quantities that you get that you think are changing due to that symmetry are not physically observable. Yeah, you look worried, and you should be. So think about that, okay? Hopefully, at the end of the course, or maybe at the end of the next course, you will understand the difference between a local and a global symmetry. So people talk about local symmetries, but I prefer to talk about local symmetries as being redundancies, because they lead to things. The things that actually change are things that are not observables. Well, the simplest example is, you did it today in the tutorial. Well, it was an optional problem, but those of you who got there, you had to show that the electromagnetic Lagrangian was invariant under a shift by something that depends on every position of a space-time, right? Well, it turns out that observables in that theory are actually observables that are invariant under that shift. Those are called gauge invariant observables. That's why I prefer to talk about that transformation not as a symmetry, but as a redundancy. Okay. But let's look at the conserved charges. So what do? We integrate d3x. Now it's convenient to raise the index, but that's trivial. We just multiply, we just raise it with the metric. And then we look at the zeroth component of our currents. And what should I get? Well, what I'm going to get, if you have the conserved charge associated with translations, that object is called the momentum of the system, okay, or the momentum operator. So this object here must be called the momentum operator. So what is P00? Sorry, what is P0? It's the integral d3x of T00. What is that in the scalar theory that we were considering, the Klein-Gordon theory? Can anyone quickly compute it? Well, look at this. We have this, right? The zeroth component is 0 here, so this looks like the definition of the momentum pi, right? And the 0 here is phi dot. So we basically have the Legendre transform. So this is nothing but the Hamiltonian, okay? Or the Hamiltonian density. And therefore, we got the Hamiltonian as the zeroth component, okay? Very good. But we know that the Hamiltonian in our Klein-Gordon theory was something of the form integral d3k omega k a dagger k ak, right? So I encourage you to go through the exercise of actually computing the other components. But after having seen this, you should be able to tell me what this thing has to be, right? What could it be? Well, the only thing that depends on the zeroth component is this object here, which looks like the zeroth component of the vector k. So this thing here should be ki okay? So exercise show this. Okay.
Question?
Yes.
In computing the three-component P, would
Yeah, you will have to do the same thing that you did with the Hamiltonian.
so the throwing out the 0-point energy?
You will also have to throw away the 0-point contributions, not energies in this case, but the contributions in that case. Now, having done this, having an interpretation of what P is, we can go back to our one-particle states. Remember, we had our one-particle states. And they were defined as the creation operators acting on the vacuum. And now there is something interesting. We can apply the full momentum operator to K. And what do we get? Well, we get the integral v3k. So we now have the full momentum operator K. We have prime here, okay? We're applying the operator, so this is a dummy index, so it should be called prime if we already have an index K here. Dagger K prime, A K prime, now acting on our state, which is a K. We can now commute this and produce a delta function that logs K prime with K together. And after performing the integral over K, what do we get? We get P mu acting on K is nothing but, so the integral logs K and K prime. This creation operator acting on the vacuum produces our state back. And we get our K mu in front, okay? So this is the basis for thinking about this as plane waves. In fact, you can ask, yes?
This is more about the previous step, but how much of this still applies if we move to general relativity and no longer
If we had a what?
if we were in general relativity and it's no longer Minkowski-based? Does this all still hold?
In general relativity, we should also be able to define an energy momentum tensor. Okay?
Would we define it in the same way, or would we make the...
Yes, it's just a field theory. It's a classical field theory.
The translation's not the same.
Translation not
So these are global translations, right? Okay. So there is something else that is interesting. Well, should I say now? No, let's actually tell you what you're going to do tomorrow in the tutorial. Okay, so I'm giving you something in advance so you can work on it today. Just as we did translations, we can do Lorentz transformations. Okay. So what are Lorentz transformations? Now we take x prime, we make a change, produce new coordinates by acting with a Lorentz transformation. So how is this thing defined? Well, it's defined as something that preserves the metric, right? So as a matrix, we can ask this to be true. And we try to find all possible matrices, 4x4 matrices with real entries that satisfy this property. Yes?
This is going back to the conserved currents, and it's about the infinite 0-point energy.
Yes.
But the way we resolve that in Hamiltonian is we just said we're going to add an infinite constant to our Lagrangian.
Yes.
And so we know that the Hamiltonian, the integral is going to converge if you consider the conserved charge. But how do you know that that same infinite constant you added to the Lagrangian will cancel the p's in the same way?
Well, very good. Check it. That was Tibro's question precisely before. He was worried exactly about that. Okay? Okay. Very good. So, but we're not interested in a finite Lorentz transformation, right? Just as we were not interested in a finite translation. We're interested in an infinitesimal transformation. So we're interested in an infinitesimal. So if it's infinitesimal, we would like this thing to be basically the identity up to something small, infinitesimal. When we plug that in here, this is something that they have done, right? That you guys have done. To plug this in here and see what this thing has to be. Right? So this is just a review, so I'm not going to do it because you have done it. So this condition implies that this infinitesimal object has to be, once you lower the index using the metric, has to satisfy this condition. It's a 4x4 antisymmetric matrix, and this implies that there are 6 independent components. Okay? So if there are 6 independent components, we should expect how many conserved charges or how many conserved currents? We should expect 6 as well. Okay. So, as I said, did I write it there? No, I didn't write it, but this is going to be in your tutorial tomorrow. So in the tutorial, you're going to work out what the conserved currents are. So I'm going to write it like this. Just to remember that this is the current index. And this index is going to be the index that labels the transformation, right? Because we have one for every entry of that antisymmetric matrix. So there are 6 independent ones. And tomorrow, you're going to show that this thing is nothing but something that can be expressed in terms of x and the energy momentum tensor that we just defined. And the conserved charges, are given by, now the conserved charges are obtained from here by just integrating d3x, the 0th component. So once again, we have one conserved charge for every transformation that we have. And therefore, they are given by we just put the 0th component there. Okay. Very good. So yesterday, Frank was worried because he could actually see that something like this was going to happen, that we were going to land on something like this. And he worried because he said, well, I know what these guys are. Okay? So if you take the space components of this, you get something like this. Remember that this is nothing but the momentum. Okay? So if you have something like this, we have pi, pj, xj, pi. And this, clearly, is the angular momentum density, and this is the total angular momentum. Of our field configuration. Now, the reason he was worried was that he wanted to know what these guys were. So let's see what happens when you have j0, when you have mu equals to 0. Of course, we cannot put a 0 here because this is antisymmetric, so there is only a j. So if we do that, we have integral d3x, we have x0 pj minus xj p0. So what is this object? Well, first of all, this is time. It can go out of the integral. Well, I shouldn't have called this P. Somebody should have told me. It's the integral that is P, right? So it's better to say that this is related to P, and it's related to P, and therefore we can interpret this, in this case, it has interpretation of angular momentum. In this case, I have T0, 0, sorry, T0J, or J0, and here I have T0, 0. Okay? Now this is time, so I can put it out of the integral, and now I have the integral of this object, which we identified with the momentum in the jth direction, minus what? Minus the integral d3x xj of T0, 0, but T0, 0 is the Hamiltonian density, right? That's what we found. So this was the Hamiltonian density. So what's the interpretation of this object? Well, first of all, what we know is that this is conserved. So this object is conserved. And what is the meaning? Well, it has kind of a funny meaning. This is the energy density, right, of your field, and you're integrating over all space weighted by xj. Well, that's exactly what you do when you want to compute the average of something in space or the center of mass of something. So this would be the center of energy of the field configuration. You're averaging x. You're averaging the energy density at each point with xj. So this is roughly the center of energy of your field configuration. And that object doesn't have to be constant in time. It could actually, the position of that object can actually change in time. But it changes like what? Well, it changes like t times pj. But pj is a conserved charge, and this whole thing is conserved. So it's telling us that that object is actually moving, but it's moving with constant velocity. Okay? So that's the interpretation of this conserved charge. It's telling you that such an object is moving with constant velocity. Okay. So now we are ready to say what I wanted to say when we got here, which is that we now have these operators, P, and let me call them, yeah, we had them there, J mu nu, okay? These conserved charges. Well, from the definition of P, it's clear that P is Hermitian. Well, it turns out that J is also Hermitian. And if you exponentiate them, you can construct an operator, say in this case, I'm going to exponentiate it with a parameter b mu, and guess what this becomes? Well, this is the translation operator. If I think here as a trivial Lorentz transformation, and here as a translation, this is a unitary operator acting on our Hilbert space, which implements translations in space-time. This is the object we define in quantum field theory 0, saying that, well, if we have a symmetry, Wigner told us that there must be a unitary representation acting on our Hilbert space. So here is the operator, the one we have over there. So we constructed explicitly the object that translates by a finite amount, and it turns out to be a unitary operator. Of course, if we act on this, on our state, we get e to the minus I b dot k. Sorry, as a 4-vector, which is precisely what you would expect as a plane wave. And that's why we get the interpretation. But you can also do the same thing and define a unitary operator that represents the action of the Lorentz group or the Lorentz generators on your Hilbert space. Okay? Very good. So last time in QFT0, we started with this, and we could actually have started with this whole thing instead of the way we started in this course. But well, yes, you had a question.
The conserved quantity. So I have in a translation 4 parameters, so it should lead to 4 conserved currents.
Yes.
In this case 6. But my energy momentum tensor has a lot more of information, right? So here you're just defining the P nu as the T0 nu component of.
Yes.
What about the other components of the energy momentum tensor?
Well, they also have meanings, and this is something that we can explore. But the point was that it's exactly the meaning as the other components of the current, right? So if you have a current, then you can write continuity equation. I mean, the fact that the current is conserved is a continuity equation, which links the J0 component with the other components.
So more than a conservation should be like a constraint
You mean what happens when you act with the other?
No. I mean, it seems somehow arbitrary that you're just taking the T0 nu component of your energy momentum tensor and define your conserved currents in this case, right? Like
no, remember that the other index mu is just an index. It could have been I, right? It could have been an index of an internal symmetry, right? I told you that it's just, in this case, it so happens that the index that labels the current has to be a vector on the Lorentz transformations. And the index that labels the transformations I'm making are the same kind of index, right? But they didn't have to. So your question is, what happens to the other components of a current? Never mind there is this current, right?
Okay.
Yes?
So sometimes this is also called the energy momentum stress tensor, and that probably is a...
Well, the other name is a stress energy tensor.
Yeah, so that's a clue about the other component that you're thinking about for the interpretation.
Yes.
So I'm not sure if so that U is an infinite dimensional object that acts on my Hilbert space. Does it make sense so this P here, we wrote it as an
operator that acts on an infinite dimensional space.
We wrote it as an integral on AKs and things like that.
Yes.
Does it make sense to exponentiate that? Would that be the explicit form of this thing?
Does P commutes with itself?
It does, so
then you can exponentiate. Yeah, very soon, hopefully very soon, we will find a case where things don't commute, and we will have to do something special to exponentiate it. Yes.
So 2 related questions. One, can you just repeat again why we can interpret that as translations, that operator's translations of the wave vector, of the plane wave?
Well, this is precisely what you get in standard quantum mechanics, right? Well, the point is that this is a representation of we just constructed it, right? We perform a translation, and we constructed the operator that implements the translation on any state of our theory. Okay? So in QFT0, we had to go the other way around. We had to assume that such an operator existed, and we declared that this was the action on the Hilbert space. So here, we just started with a quantum field theory, and we derived the operator. Okay?
So my second question is more abstract, but it seems like that it's somewhat circular, which is a good thing, in that we first, we got the generators of the algebra or of the group by acting with infinitesimal transformations.
Yes. That's always the way you do it.
Okay.
If you want to understand a Lie group is a manifold. It's a very complicated object. And the way we always handle something that complicated is to go to the identity and explore the tangent space and explore what happens very, very close to the identity, and hope that understanding that allows you to move ahead in different directions and construct the whole object. So that's
how is Noether's theorem related to Lie groups? I mean, is that?
Well, the connection would be absolutely zero if these Lie groups that we are considering were not symmetries of the Lagrangian. They are continuous symmetries. Right? Lie groups are continuous objects because they are manifolds. Okay? So that's the connection. Every time you have, if a Lie group is a symmetry of your Lagrangian, you will have conserved currents because it's a continuous object. And Noether's theorem told us that we can construct conserved charges every time, or conserved currents, sorry, every time you have a continuous symmetry.
Can you prove that those charges are always the generators of the, are always the generators?
Yes, exactly. That would be a second part of the theorem. Not of Noether's theorem, but it would be something else. It would be that these charges are always, that's a very deep thing, in fact, that the charges are the generators of the symmetries. Yes.
One thing, so we're defining now this U of zero lambda as the Lorentz transformation of your vectors of your Hilbert space, right?
Yeah, U zero, the zero means that there is no translation.
Right, so if
yes.
I'm not mistaken, we did this in Q of T0, and basically the action of U0 lambda is just Lorentz transforming your weight vector, right?
Oh, excellent. That's a very good exercise. Yes. So you should show that that's what happens in this case.
I mean, it's not obvious from the definition of your G mu, right?
Well, that's why you have to do it. Yes.
Okay.
Yes. Okay. Very good. Yes. So this is very efficient. While you ask questions, I resolve it.
So the procedure, so everything up to the last point that just got covered was purely classical, right? So was the procedure basically that we realized P mu was the generator of translations classically. So we say that when we go over to the quantum case, then if we just promote P mu as an operator.
That's also a very deep question. It could be that something goes wrong when we go to the quantum theory. And when it does, we say that we found an anomaly. So an anomaly would be a symmetry of the classical theory that for some reason the quantum theory decides not to respect. So that could happen, yes.
So was that last step like a definition of the translation operator acting on the Hilbert space, or did it follow from something where did this? So we did everything classically up to here, but then
yeah, but then this P mu was given in terms of phi and pi dot, right? I mean, we could just construct it. I mean, I didn't. Once you have the Lagrangian, you can construct it. And now you can say, well, let's replace these guys by operators, the operators we have. And then you would find the formula that we got. Okay, so the reason I'm bothering to erase everything is that we're going to start something completely different now.
So you said that the conserved charges give you the generators of your group, but what happens if they don't exist?
If they what?
If they don't exist, the inputs diverge.
Then there is no representation of that object on your Hilbert space. But it doesn't mean that you cannot constrain your theory. There is still the conserved currents, and they will lead to constraints on what we're going to define today, which are the correlation functions. So you can still learn many things about your theory, or constraints about your theory, coming from, oh, that reminds me, yes. We said that when you have a discrete symmetry, you cannot have a conserved quantity, right? Because the discrete symmetry is not a continuous symmetry. But still, we're going to see that it can constrain very much what happens to your theory. For instance, just to give you an example, imagine that you're constructing in this particular case, the interaction of these Kaluza-Klein modes, right? This Kaluza-Klein field. And you ask, well, can I scatter 2 Kaluza-Klein fields and produce 3 Kaluza-Klein fields? Well, you would say clearly no, because our theory is free, so that would be impossible, right? But we're about to study interactions. So when we study interactions and interacting quantum field theory, you can expect things to happen like that. And now, if there is a discrete symmetry of your Lagrangian, like changing the field by minus itself, because everything that you write down in your Lagrangian happens to be quadratic or be an even power of the field, then, exactly, it's impossible to produce from two fields, you scatter two fields, it's impossible to produce three or any odd number. So discrete symmetries will also be very important, and I hope that at some point we can discuss them. But in order to do that, we cannot get any mileage unless we study interactions. So that would be the next step, okay? In order to actually start seeing the use of everything we're doing, we have to study interactions. Okay. So we have to start somewhere. We want to describe an interacting theory. Well, a reasonable place to start would be with a theory that we understand already. Okay? So let me actually put this. This is our Lagrangian density for our for our Klein-Gordon theory. And we can ask, how can we mess around and make this more complicated? Okay? Well, clearly we can add things here that can make the equations of motion nonlinear and complicated, right? So as you pointed out, when I first derived these equations of motion, I had a typo, and I put a square. And the equations of motion that I had were nonlinear, but the equations of motion that come from here are linear, and that's why we could solve them completely. So we want to make life more complicated by adding terms that will make the equations of motions nonlinear. So in order to simplify our lives, we're going to start by adding terms that can be just powers of the field, okay? By convention, and you will see that it's very convenient, actually. People normalize this with an n factorial if you have n powers, just to match the half that you had here. Okay? So these lambda m's are called the coupling constants. Of the interactions. And note that we did something very important in writing this. First of all, we neglected anything that had derivatives. So that's actually to make our life simpler. But the second is that all the interactions happen at the same space-time point. Okay? So you could say, well, how could you have had something else? Can anybody think something else that I could have written there? Yes?
Why is there no linear term on 5? You're just considered for powers bigger than 2, right?
Yeah, linear term in 5, I can always reabsorb it by a field redefinition, by changing what I mean by phi. Just shift phi, and you can absorb it. Okay? So that's not interesting. So could I have done something else? Well, yes, I could have added to the Lagrangian something that looks like this, say, integral d for y. I mean, just to say something crazy, I don't know. How about this? Yeah, that would be a little crazy, but yeah, I could have done it.
So about locality?
Yes, so things like this, when we only add terms like this, we say that we're adding local interactions. Okay? Very good. So we have our local interactions. Now let's do a little bit of dimensional analysis. I'm going to do dimensional analysis in assuming that our space-time is 4-dimensional, but I would like you to try everything that we're going to do now, assuming that the space-time is d-dimensional. Okay? So let's keep that in mind when we do this. In fact, you could, as you take notes, you could try to do it in d dimensions. How about that? So let's start with the action. We know the action is d for x, L. So what I want you to do is to put a d here. Okay? We can establish notation and say that when you want to generalize this, you can call this capital D. Okay? In fact, should we do it or should we? Yeah, maybe we should do it. No, maybe we shouldn't. Okay. So you should do it. So let's do this. So what are the units of the action? The action has units of angular momentum, right? But so does h bar, and we're setting h bar to 1. So the action is dimensionless. If that was too fast, then sit down and actually check the dimensions of the action. And remember that we're setting h bar and c to 1. So the dimensions of the action has dimensions of mass to the 0. That's how we say it. Now, everything has dimensions of mass or dimensions of energy, which are the same thing. Okay? Now, we're interested in the dimensions now of the Lagrangian density. But in order to find the dimensions of the Lagrangian density, we have to find out the dimensions of the measure. The measure has dimensions of mass to the -4th, right? Because it has dimensions of length to the 4th, but length goes like 1 over mass, so it's mass to the -4th. Therefore, the Lagrangians should have dimension 4. And if we look at the action, we can find out what the dimension of our scalar field is. So the dimension of this thing is the same as the dimension of this thing times the dimension of this thing. And therefore, we get, this one has dimensions of 1 over length, so this one has dimensions of mass squared, right? Whatever the dimension of this thing is, let's put it here, the dimension of phi has to be equal to the dimension of the Lagrangian density, which is 4, and therefore the dimension of phi must be, sorry, there is a 2 here, right? So this is 2 times the dimension of phi, and therefore the dimension of phi has to be dimensions of mass. Okay, so if that's the dimension of this object, what is the dimension of the parameter we put there and we call m? So now, we followed Tibra's observation last time that maybe in the interacting theory, this object, oh, there are many things that are called m here. This is a really bad, it's not such a good thing. Maybe let's call it n now. So let's call this m0. Because now we're not sure that that parameter will have anything to do with the masses of the excitations or the particles of our theory. Before, in the free theory, we found that these guys were actually the masses of the objects, right? The dispersion relation was k squared equals to m squared. So m, that parameter, was the mass. But now it's just a parameter. We don't know if it's going to be the mass. So the dimensions of m0 are also dimensions of mass, at least in the classical theory. Well, I would have to say at this point that in the quantum theory, even the notion of the dimensionality can be shifted. But let's not get into that at the moment. And what are the dimensions of the coupling constants? Can anybody work them out? To the fourth minus n, is that? Looks like, right? So if you put it there, yep, that's right. Very good, very good. Okay, so something interesting happens is that if we want to consider our theory, we probably want to know what happens. I mean, now these particles are interacting, so we can imagine scattering these particles and thinking that whatever controls the interactions or how important these interactions are will have to be some dimensionless parameter, right? We cannot talk about dimensionful parameters and say that they have any meaning when we say that they are big or small, large or small. That doesn't make any sense because it depends on your units, right? So we want to think about dimensionless parameters in order to understand if something is important or something is not important, okay? So that's a very important lesson, which is that we always want to think about dimensionless. But most of these couplings, yes?
Can you unpack that statement a little bit more? For example, energy is an important physical quantity that is dimensional. Oh, I guess that's not a parameter, right? So that's a quantity.
Well, it all depends on what you're talking about, right? If you say the vacuum energy, is that important? If I don't consider gravity or any boundary effects, no, it's not important. Only the difference is important. So just 1 second. Okay. So if we have an interaction, okay. So we can define, say, the energy of this interaction, okay? The center of mass energy, that would be a quantity that we can define. So the center of mass energy is given by, say, if these were particles PA and PB, it's given by PA plus PB squared. And this is what we call in QFT0 S, okay? So this would be the energy square is controlled by this parameter we call S, okay? Now, when can we say that this interaction is important, the energy is high, or the energy is small? Well, once again, we should look at the dimensionless parameters. So what are the dimensionless parameters? We should look at the couplings in our theory and decide how they compare to the energy of our interaction. So the dimensionless parameters, we have to be powers of the coupling times powers of our energy in order to make them dimensionless. So the energy has dimension of mass, and therefore, to make this dimensionless, what do we have to do? So let's call lambda hat the dimensionless quantity. So we have to multiply by m minus 4. Okay? So that means something very interesting. It means that if you're considering scattering processes, okay, where the energies are energies at which we perform experiments, okay? So just to say, when do you call something large or small? Now, energy goes like 1 over the length, okay? So I'm going to define small energies, right? Something that has to do with length scales of things that we do here in our classroom. Of course, we could even define lower energies by saying things that happen in galaxies, and even lower energies by things that happen at the scale, at the Hubble scale, okay? And I'm going to define high energies to be things that happen at very short distances, things that happen at the scale, say, of gluon interactins, okay? So let's actually decide what happens to these couplings, or which couplings are important when we take the energy to be large and when we take the energy to be small. So when we take the energy to be small, and then by small, I'm saying the scale of a human, say. So that's my definition of a small. Of course, somebody who lives at the scale of a galaxy would say that that's stupid. That's very short distances, right? But we happen to be here, so we can define it. So if we do that, then which couplings are important for us? Which are the coupling constants or the interactions that we will be able to measure and see? Well, what do we get? Well, if n is greater than 4, then what happens to the interactions? Yeah, this is very small. If n is less than 4, then these are large. And if n is equal to 4, then we get to choose. Okay? So people like to call these interactions that are small at our energies and therefore don't affect very much what we see or what we do at experiments. They call this, and it's a good name for this, irrelevant. It's very appropriate, the name. How would you call these ones then? Relevant. And how about these ones? Borderline. They are actually called marginal. Okay. Well, is this good news or not? Well, it's a lot of good news because you see, out of all the infinite number of interactions that I have to write down there, only very few satisfy this and this condition. In fact, only 2. So that's very good. So that explains that, in principle, we should only worry about a Lagrangian, or the most important Lagrangian that we have to worry about, really, is something of the form okay. In fact, the complex version of this Lagrangian, okay, when the scalar field is a complex scalar field, is exactly, well, 2 copies of that produces exactly the Lagrangian of the Higgs field. And the Higgs field, in fact, has these 2 interactions because they are allowed, they are relevant or marginal, and they must be there, and they are there, in fact. So in this course, we're going to assume that this is not here. But if we were working in 6 dimensions, I mean, I'm not going to consider this guy. I'm just going to consider this one to make our lives simpler. This one is the marginal. This is dimensionless. But if we are in 6 dimensions, who is the marginal operator? Who is the marginal interaction? Yeah, there are only 2 possibilities. Either you go up or you go down. So you go down. In 6 dimensions, this guy is the marginal one. So in 6 dimensions, if this lecture was given in 6 dimensions, we could just consider this guy. Wouldn't that be fun? You can just forget about all this and life would be a little bit simpler. Yes?
So getting rid of that term, it's not the same as putting like a symmetry by hand. I mean, you're making your Lagrangian even.
Exactly. That's very good. So if we impose, or suppose that you have a theory where you measure things and you say, well, I have never seen 2 particles, two of these scalar fields producing an odd number of guys. Then you immediately realize that there must be a symmetry that prevents you from producing an odd number of guys. And you will write down a Lagrangian like this and say that the Lagrangian must have this symmetry, and therefore this must be forbidden. Exactly. Yes.
I missed the reasoning as to why you chose not to include like higher derivatives, so you can take away some energy powers. On the
Well, try to include higher derivatives and see what happens to the dimension, to the couplings. Okay, that's an exercise for you. Yes.
Can you explain again why we only want dimensionless parameters like lambda hat?
Well, it's only to say that when you compute this, right? When you compute any scattering process or any physical process, the relevant scale, the relevant dimensionless scale, dimensionful scale is the energy. So if you want to know, I mean, I'm not saying that the Lagrangian couldn't have all the other terms. All I'm saying is that when you want to compute this at energies that are the energies that are small, so that they are relevant to the experiments we do, then all those interactions, after working a lot, you will find that they enter here through these dimensionless couplings. That's what I'm saying, that after you sit down and work for a month, you will find that all these things, you compute this, and the way these couplings enter are exactly through this combination. Then when you plug in the energy that you were interested in, you say, oh, shit, all that work, and those guys didn't really contribute anything to the calculation I'm doing. Okay. Yes?
So you're saying when if you raise the dimensionality, you need fewer and fewer terms. Does this mean string theorists get to do really simple field theory?
No, life actually gets life gets. That's a long story. No, it's not. In higher dimensions, what you get are things that are called effective field theories. And well, that's a long story. But the answer is no. It's not that when you go to higher dimensions, life gets simpler. Okay. In fact, life gets more complicated.
So was this symmetry the reason that you initially chose to ignore the phi cubed term, or what was the justification?
Well, the reason is that we have to do something simple in the course so that we can finish. But this could be a good reason.
Okay.
Okay, so let's impose from now, of course, this was the reason from the very beginning. There is a symmetry, and therefore that prevents this from being there. Yes?
How do we know in the first place that a priori these terms correspond to interactions?
Oh.
Why are phi cubed terms as part of the fourth term's interactions?
Well, simply because you can take this as a classical field theory, right? And now take your classical field theory, compute the analog of the Euler-Lagrange equations for this guy, and then you get nonlinear terms.
Yeah.
So you can now pretend that this coupling is very small and start to solve this in perturbation theory, right? The classical field theory. You start to solve this in perturbation theory, and then you would see how your Fourier modes, when you span phi, the first time you span phi, right? You would say, well, my first approximation would be this equal to 0. So you have the free theory. Then I have to plug it into this guy, right? And see what the interactions are. And see what the next term is. When you plug it into here, well, it's not going to be phi to the fourth. It's going to be phi cubed, right? In the equations of motion, because we have to take a derivative. When you plug that in there, you find now something that has lots of oscillators multiplying themselves. That can be interpreted as something that mixes objects of different Ks. Well, imagine now that operator acting on your quantum on the vacuum, right? That operator acting on the vacuum will now produce lots of particles with different modes. Yes, but we're going to see that explicitly, so don't worry. That's the reason you're here.
Is there any reason why you chose the lambda force to be positive, or the lambda n to be positive and put a minus sign there?
Well, I could ask you that, and you should answer it now. So why is lambda 4 to be positive? Why do I have to? Yes, the Hamiltonian. Right? Otherwise, the energy would be, I will have negative energies. And then it would be more favorable to produce particles instead of being difficult to produce particles.
But I was thinking, like, I mean, those phi-4 terms or the phi-square term, some term. I was thinking of the potential that you have to your Lagrangian, right? And for example, when I have a Coulomb potential or something, that is a negative potential, right? Or it depends on the charge that generates, right? Either if it is an attractive or a repulsive potential.
Your Lagrangian is always kinetic term minus potential, right? So that's the potential in this case. So that's why this thing would be the equivalent of the potential. Okay, so let's move on a little bit. So this was a nice discussion, but let's actually try to figure out what to do with this object. Maybe let's try to be consistent and put an M0 here again. So what do we do? So we all remember, yes?
So I mean, just what I'm just saying is that one of these positive parameters becoming negative or imaginary is exactly what happens in spontaneous symmetry breaking and the Higgs. But that's a long story, right? So because in the
the total object is positive.
Exactly.
Yes. No, well, what Tibra is saying is that if you keep this term, and this is non-zero and positive, this term could be negative. But that's no problem, right? Because the total energy for large field configurations will still be positive. But you don't want this term to be negative. So that was your question. Why couldn't you have this guy to be negative? That would lead to a theory that has, say, infinite heat capacity. So all kind of sick things will happen. Okay? So so we're going to think, well, actually, that's the only thing we can do. We're going to do exactly the only thing we can do, which is to treat this as a small deformation of this. Okay? So we're going to do perturbation theory. Okay. Now, last time, for the free theory, you guys check today that the Feynman propagator was a Green's function. Was a Green's function of the Klein-Gordon operator. Not only that, this object played a crucial role in our scattering amplitudes in QFT0. That's why I was so excited to get to this guy, because we could finally construct it from the fields, okay? Something that we derived from unitarity and was very important. Now we're going to concentrate, or the goal of this week, actually, the goal of this whole week is to find the analog of this object in an interacting theory. So let me call these guys free here. Just to remember we did this in the free case. So the goal is to find out the analog of this Green function for our interacting theory, okay? That seems like a reasonable goal to achieve. Especially in the last 10 minutes of the lecture. Okay, so what do we need? We have to make some assumptions to start working with something, right? So let's make some assumptions. And if you're not happy with any of these assumptions, well, I'm sorry, but we cannot do anything. So the first one, is that in the interacting theory, so these are assumptions about our full interacting theory. So the first assumption is that there exists a Hilbert space The second assumption is that in the Hilbert space, there exists a state unique state which we're going to call omega, and it's a state of smallest possible energy, so we're going to call it the ground state. Okay. The third assumption we're going to make is that since lambda is small, we're going to take it to be very small, lambda 4, it's reasonable, the following assumption is reasonable, that the vacuum of the free theory is a state in our Hilbert space, let's call it H, okay? And not only that, but it has a non-zero overlap with a true vacuum. Yes.
One thing with respect to lambda form being smaller than 1.
Yes.
You motivate it here in terms of the scale of the energies.
Yeah, put n equals 4.
Exactly.
What happens?
So if it is marginal, shouldn't lambda 4 be a order 1 instead?
Definitely not. Look what I wrote here.
We get just talk about.
I mean, I thought about it. And once again, since I'm giving the lecture, I choose to be very small. In your own time, you can choose it to be large. Okay, very good.
But if I continue, why would it be important to have the ground state to be unique? Like,
It's a technical assumption, and we will see that otherwise life will get complicated. Sometimes it doesn't happen, okay? Especially if you have supersymmetric theories, the ground state doesn't have to be unique. Okay.
So, one thing with respect to this spectrum, the vacuum of the free theory is basically a state with no particles at all. How should one interpret then the vacuum of the interacting theory?
No, sorry. This thing, we don't know what it is here. It's just a random state. It doesn't have any meaning, really.
All right, okay.
I mean, any physical meaning. Of course, when lambda is very, very small, we expect that in some sense, the overlap of this guy and this guy should not be very small. They should have some non-trivial overlap. But we cannot interpret this state as being something where we have no particles. What do we mean by particles? Particles should now be things that come from the true vacuum of the theory, right? But that's part of what we're going to do. So the goal is to study the analog of the Green's function, but now for the full interacting theory. So in the case of the full interacting theory, what is the thing we have to compute? Well, we don't have to compute that. That's right. So this is the object we want to compute. And how do we start and compute it? Well, you stare at it for a while, And then you say, well, I have no idea what to do. Then you start, then you really have to do something smart and say, well, since I'm very, very close to the free theory, maybe I should try to express everything that is given in this formula in terms of quantities that come from the free theory. If I succeed, I'm in business, because we're all experts in free theories. Okay? So that's what we have to do. So we have to find a way of expressing everything in terms of a free theory. Now, imagine that we have our fully interacting field, okay? And we take a snapshot of this guy at a given time. So take this, and now take a snapshot at t equals to t0, okay? So that thing will look like something. Okay? So you see it there. Now what we're going to say is that, well, that configuration at a given time could have very well been the initial conditions for the problem we had before, the problem we had yesterday, of a free theory. Okay? So this thing could have very well be the T0 snapshot of our free theory. Okay? And if that's the case, well, then we can Fourier expand this in terms, we can just find the Fourier transformation of this. And the Fourier transform is something that looks like this. So I'm going to write here, let me write it like this. T0 omega k minus k dot x plus a dagger k e to the I T0 omega k minus k dot x. Yes?
So I can imagine that for a classical field theory where the fields actually have some value, but in a quantum field theory, they're operators, right? So what does it mean for the snapshot of a field?
Well, exactly the same thing. At every point we have an operator. We're going to model that by operators from the free theory. Exactly the same snapshot. It says that you need a better camera to do it.
Sorry, I'm not sure I understood. Are you saying that at one particular point I can write my field in terms of those A's and A daggers are supposed to be the guys from before?
Yeah, these are operators. These are operators that happen to be exactly the Fourier modes of this field configuration. So I'm basically saying that any field at a given time, I can expand it, well, it's a technical assumption really, to say that these fields, which are distributions, can be Fourier transformed at any time in space. That's all that I'm assuming, right? Any field can be Fourier transformed. And whatever the modes that I get, I'm going to call them A and A dagger. Especially because it's a real field. So this is something that I can definitely, this guy has to be A dagger, no matter what the field is. So are you happy now with that? So it's a field, and I'm just computing the Fourier transform of that field. So there must be a representation in terms of other fields, which are these guys, such that this is true. I'm just taking the Fourier transform. I'm assuming that the Fourier transform exists. So what you're saying is that when they are fields, maybe it's not guaranteed.
I know that in the Heisenberg representation, that works because the operator equation in the Heisenberg. So in the interacting picture, it works. But in general, in a general picture, anyway, we can. No.
This is very important. You cannot be unhappy about this. You agree that at T0, this is this is a field. This is there is an operator at each space-time point, at each space point. Can you take the Fourier transform of that thing?
Yeah.
Would it look any different than this?
No.
Isn't this the most general Fourier transform?
Yeah, that's I agree.
Yeah, but would the A's depend on T0 in general?
No, I'm just doing that at T0. I'm calling these A's the ones that I got by doing the Fourier transform in a space of my operator at that time.
Right, but you might get different A's if you do it at different T0, like different T's.
Yeah. Okay. So now this is a different question.
Yeah.
How do you evolve this thing?
Right.
Well, good luck with that. We don't know, right? I'm doing something that has no science whatsoever. I'm saying I have no idea what to do with this thing, but for sure, at a given time, if I fix the time, I can write down the Fourier transform of something that I don't know in terms of things that I don't know.
So is it also assumed that the Hilbert space in which the free fields live is the same Hilbert space in which the interaction fields
No, I'm not really assuming that. I mean, these guys, I'm using the same notation because this is the notation for the Fourier transform modes of any field, of any object. That's the name I'm giving them. Yes.
Can this be motivated by saying that we're looking to it for scattering processes, right? So that I know that at large distances, I have no interaction between my field, and basically I can apply what we learned from free field theory, and then by means of the evolution operator, get the interaction inside.
No, that's not what I'm doing.
No, but
I'm really not doing anything. There is no science in this.
it's true.
This is okay. No, I mean we could do many other things, but I chose to start with this, so I thought it sounded reasonable.
So do A and A guys satisfy the same combinational relation? Yeah.
We don't know what they do. We don't know what they are, right? Okay, very good. But whatever it is, okay, our field, what we know is that the full field, the full interacting field, right, would be obtained by our snapshot value by evolving this with the full Hamiltonian of the theory from time t0 to the time t. That much we know. How do these guys, how does the full Hamiltonian, what is the full Hamiltonian? How does it act on these objects? We don't know. So since we don't know, so now we don't know, what to do with this. So let's do something. Yes?
So you don't even know if your Hamiltonian is independent right now.
Or we do.
I said we don't know anything.
Right.
So I'm not going to do anything with this at the moment.
Okay, that's
I'm saying that if life was nice and we knew more than we do, this would be a good thing to do. I mean, this would be the definition of the evolution of this guy, right? No, we're assuming that, I mean, our theory, okay, sorry, I was thinking about something else. But our theory is Lorentz invariant, right? So we must have the energy, we must have conserved quantities related to translations in time, and that quantity is the Hamiltonian, okay? But still, that doesn't help. We don't know what this is. So let's do something that we know. So instead of doing this, let's take our operator here and now evolve it with a free Hamiltonian. After all, that's the thing that we know how to do, right? We spent all this time up to today learning how to deal with this, okay? And we're going to call this, or people like to call it, the interaction picture operator. Okay? And we're going to end the lecture by simply saying the following, which is, again, completely useless at the moment. Well, the first thing is that if this is the object we have, right, and we evolve it with a free Hamiltonian, we should be able to obtain what this field is at any point. So this is something that is given, and we know what it is, but it doesn't seem to be very useful. Now we're going to end the lecture by writing a formula that also looks as if it wasn't very useful, but it's the following. We can now write the full field, okay, as follows. E to the I h t minus t0. I'm going to put here phi of t0, and I'm going to put here e to the minus I h. And the reason is that I want to introduce the identity here and the identity here, okay? So I'm going to introduce the identity operator, but I'm going to decompose it as e to the I h0 t minus t0 and e to the minus I h0 t minus t0, and do the same thing here. So note that this is just the identity. I'm going to do exactly the same thing here, but with minus h0 and e to the I h0. Okay? Why did I do that? Well, because then this object is exactly what I define as my interaction field. And still, this thing that is here is an operator, is a unitary operator, which I can call UTT0, which is unknown. We don't know what it is. But at least we get a very elegant looking formula in terms of things that we don't know. Because this is the dagger of that operator. So we get a very nice looking formula, which is that our interacting field is nothing but evolving or acting on our field, on our interaction field phi by this operator u and ut. Okay? So tomorrow, we're going to study how to find this object. And if we succeed, then we're in business, because then we can compute our fields, and they will go into here, and then we only have to deal with a vacuum. And learn how to deal with a vacuum, put it all together, and declare victory. Okay? And hopefully all that's going to happen tomorrow. Okay, let's stop here. I think it's a